It's indeed a great pleasure for me to speak to CUSAT, the Cochin University students, and I hope there are probably one or two other students might also be there, but Cochin University students mainly. And it is always a great pleasure to talk to students, and particularly from your university. So I'm very happy to be here for this talk, and I'm going to speak about something which is always fascinating. It looks simple to state, it looks simple to understand, but it has very deep uh, connections to fundamental physics, as well as in terms of applications and in terms of understanding itself. So with that, I'm going to share my screen about the connection between spin and statistics. It looks very simple to state, and in my opinion, it is very profound. So with that remark, I'll tell you what is it I'm going to do. So this is a very deep subject which has bothered a lot of people, starting from giants like Albert Einstein, Fermi, Dirac, von Neumann, various people. And if you really want to know whether we have a good understanding, even now there are still problems and open questions. So with that, I'm going to leave it and then start with the talk. So I have planned. I'm going to describe what is spin, and I'm going to talk about the spin of photon, which is light, electromagnetic radiation. And I'm also going to talk about the spin of electron, which is something which we knew for the past 150 years. So then we knew one result, which is called the statistics of bosons and fermions. And particularly, they were introduced for photon and electron initially, and escalated to other things. So I will talk about the statistics. And there is a connection which is going by the name spin statistics theorem. I will tell what is the theorem and how it is proven. I'm not going to prove it to you, but I will tell you that how these things come about. And probably Ramesh Babu will, when he does tomorrow quantum field theory, he will mention that, and he will probably use it also. But I'm not going to use quantum field theory for this, and that is the whole idea about this whole program, about spin statistics theorem or spin statistics connection. So what is it? There is a mysterious law, theorem, that is used in quantum physics, and the logical understanding of this still eludes our minds. It is known as spin statistics theorem. It plays an important role in several areas of physics. In fact, I have started wondering even in some of my questions in astrophysics. I will probably mention it. I have not written it up in this, but I will mention it. And in high energy physics, astrophysics, condensed matter physics, quantum optics, and various other places. I will explain the meaning and the context of the theorem, as well as point out some uses. I will elaborate the topological origin. There is a topological origin of this theorem, and it is very simple. And how it can help us to go beyond to what is now known as non-Abelian statistics. First, I will explain the term spin and then statistics. Then I will explore the connections between them. Okay, so what is spin? Now we all know electron. Electron for the past, after maybe 120 years or so, when the gas, mercury or hydrogen was heated, and then electric field is applied, then you find the electrons come out of it and try to give us some light. So the electron is well known. Its mass is also well known. The mass, I will give you the mass in MeV, which is million electron volt. You can even give it in terms of grams. and that is 0.5 million electron volt. That is the mass. When it is at rest, if it is at rest, it has a mass and it is 0.5 MeV. Now, when it is at rest, it has a charge, and everywhere, even when it is moving, it has a charge. So there is an electric charge which is negative, and it has some value, probably some 1.6 into 10 power minus 19 coulomb or something like that. But these two are intrinsic values to the electron. Electron, if you want to identify what is electron, you have to give me the mass and the charge. Okay, these are intrinsic ones. It can have momentum. It can have angular momentum. It can have velocity. And it can have energy, more energy. And these are all external to it to describe the state of an electron, a dynamical state of an electron. It has momentum, angular momentum, etc. In addition to this, there is a property and which looks like angular momentum, but it turns out to be it is intrinsic. It is intrinsic to the electron itself, like electric charge, like mass. It is intrinsic. If you want to characterize it, it has this value even when it is at rest. Even though it looks like it is angular momentum, it is intrinsic to it. So it is called the spin. We can visualize this like Earth, which is a big body of about 6,000 kilometers radius, and it is rotating around the sun with an angular momentum, and also it is spinning around itself. In 24 hours it spins, so from morning to evening and then night, and the next day is coming. So we count the days based on its rotation about itself, spinning of the Earth. But the size of the electron, we don't know. It is zero size, or what we know is less than 10 to the power minus 18 meters. So tiny size, I don't know, we can associate like Earth spin. We cannot associate like that. We can't talk like that. But still, it has this quantity which is called the spin. So we take it as intrinsic one, which is at rest. So when Earth is rotating, it is not at rest. Of course, it is moving. But even if you ignore that movement around the sun, it is still rotating. So it has some dynamics. But here, there is no such thing. Even when it is at rest, it has this value. And this is the important part. Even when the electron is at rest, we need three quantities to specify what is electron. The identity of electron is given by the charge, it is given by the mass, and its spin value, which is half. Okay. How do we know it is there and what is its value? So the first way in which it was discovered was due to an experiment done by Stern and Gerlach in Germany. This is about more than 100 years back. Since the electron has charge, it is affected by the magnetic field when it is moving, and it has a magnetic dipole moment. Okay, so magnetic dipole moment, which one can actually see. So this is the experiment which was done by Stern-Gerlach experiment. So what was done? There is an oven where electrons are produced, heat something where electrons are produced. A beam is coming out of that small hole which is there, and there are magnets which are kept in its path, and the magnet is going from north to south. It is in the z-axis. So there is a south or down, and north is above, and there is an z-axis which is joining them. So the z-axis is the direction of the magnetic field which is there. So because of that, electron beam, which has supposedly having spin half, it has magnetic energy, which is mu dot B, magnetic moment. So it can have up and down value, and it splits into two, and there is a screen in which it hits. And the screen, all the up spins hit to the top portion, and the down spin hit the bottom portion. So this is how the experiment was done, and I have represented it schematically. It is much more deeper than this, but schematically this is what I have given. and this is the way in which the electron spin was understood right from the beginning. So there is an association of electric charge, the mass, and the spin, which is supposedly, it produces two states, spin up, spin down, spin half is the thing. Now, I have given the next diagram. It is a quantum mechanical object. We cannot understand this spin half in a non-quantum mechanical context. So we have to understand it, otherwise angular momentum quantization will not come. So the spin angular momentum also is quantized, spin half, spin up and spin down. In this diagram, the beam is coming from the left and then it is split in the z-axis. One is going above and one is going below. Now the one which is going above, I now apply along the x-axis. Okay, I apply magnetic field along the x-axis. Now we have to talk about the spin up and spin down with respect to the x-axis now, because that will have, again, half of them will have spin up, spin down with respect to x-axis. So that is again split, and that is what the diagram is telling you. And it is very profound that quantum origin is seen, and even though it is spin up state, we can even, with respect to z-axis, we can think of that as superposition of spin up and spin down from x-axis or y-axis, etc. We cannot define exactly like that. So we can tell only about the z-axis or one axis, and then this is what is used to talk about electron in the earlier days. Okay, that is for electron, which has spin, which has mass, which has electric charge. Now I'm going to talk about another particle, which is spin 1. You can ask me, why don't I talk about spin 0? At least at the times when we were talking about all the particles in the last 100 years, there was not a single particle known with spin 0 particle at that time. Elementary particle, I'm talking about elementary particle. So spin 1 was also not known at the time when the electron spin was discovered, but this is very surprising, and this is related to a story which I'm going to tell, which is also interesting, in which one of our Indian physicists was involved. Apart from electron 100 years back, the most important particle was photon or light. Now, 1900, when Planck derived his formula for black body radiation, he needed that radiation energy is exchanged through quanta. You cannot understand that continuously energy is being absorbed and released. So he needed they are being absorbed or released through quanta, which is in the quanta of h nu. And nature of light as wave changed to that of particle. This is about 1900s. Strengthened by Einstein's 1905 paper explaining photoelectric effect, it was clear light exists as particles because you needed the particles to knock out the electrons. To knock out the electrons, you need these particles, which are photons, okay? And the energy given by that E is equal to h nu. So this is what was 1905 paper, the famous paper written, one of the four papers were written at that year of miracle, and one of the paper is about the theory of photoelectric effect. This is in 1905. The radiation, he said, is not only exchanged, the energy is exchanged not only through quanta, it exists as quanta. So this is the most important contribution coming from that remark of Einstein, that light exists as quanta even in normal state. This is the basic idea. Okay. 1925, 20 years later, Satyendranath Bose in Dhaka, not in India, well, in those days it was India because Bangladesh was part of India, British India. Satyendranath Bose wrote a paper. He explained that black body radiation as through quanta of light. The quanta of light is photons as a gas of photons. You have a gas enclosed in a volume, and like kinetic theory of gases. So unlike the earlier gases like hydrogen or other things, etc., you have now photons as a gas inside, and the photons exist as particles, quanta of light, and applied statistical mechanics for it. So he applied statistical mechanics for it. Now, he needed two things for this. One of the most important thing which he introduced at that time was he derived the formula for the black body radiation, and then he needed a factor of 2 was required for him. So what he said was, okay, the photon has a spin, and the spin value is, it has 2 degrees of freedom. For him, he said the spin has 2 degrees of freedom for the photon, and he multiplied by the factor of 2 and then wrote the paper. Another term which is used is what I'm going to use next. But before that, let me explain the controversy even here. This spin, which was introduced by him, spin, he called it has spin 1, but has 2 values, and plus and minus if you want, and then he used this concept. Now he's tried to publish that paper. That paper, when he tried to publish it, it was rejected by well-known journals at that time. And he was very frustrated because he was getting the black body radiation correct formula, and everything was falling apart as kinetic theory of gases. And he was very happy with that, and he sent it to the journal and they rejected it. So when it was rejected, he had a almost worshipping association with Einstein. He has never met him. So he wrote to Professor Einstein, dear Professor Einstein, I have written this paper on the black body radiation formula as a gas of photons, okay, to explain this thing, and I could derive this formula. Einstein was very happy with that. But he was very unhappy with one term which was introduced by Bose, and that was that the spin. Because the spin you associate with particles, right? You associate spin with particles which spins about itself or anything. But it was unheard of to call about photon and its spin at that time, and even to Einstein. So he removed the term spin from that paper of Einstein and used polarization states. But as you know, polarization is a wave phenomenon. It is right circularly polarized or left circularly polarized or polarized along x-axis or y-axis. So this polarization, he added 2 terms. That's how the original formula was also discovered. So he used the term polarization instead of the spin and translated the whole paper from English to German and was published in Annalen der Physik by Einstein on behalf of Bose, Jagdish Chandra Bose, or not Jagdish Chandra, Satyendranath Bose. So it turned out Einstein was wrong. There is one place, of course, several places he was wrong, and Einstein was wrong in this place, and Bose was right, because photon has spin 1, and the spin is described by helicity, and now we know, and it has 2 degrees of freedom. And this is a very important thing for this thing. And what Einstein was the next stage. Next, it goes to the issue about statistics. Now, I introduced the spin for photon and electron. Then I'm going to introduce the statistics for photon. So in order to derive this particular black body radiation, Bose introduced another very, very interesting concept. That is what impressed Einstein, and that's why he was very happy to translate the paper and publish it on behalf of Bose. Bose introduced another interesting concept, namely the photons with the same momentum and energy are indistinguishable. They are one and the same, okay? That means the state will be the same if you exchange any 2 of them. Okay, you take any 2 photons of the same momentum and energy, and you will exchange it, You should not count it as two different states, but you should count it as one state. This is the combinatoric factor. In statistical mechanics, whenever if you have been taught statistical mechanics, we have to compute the number of states, and when you compute the number of states, you have to use this fact that two states which are identical, indistinguishable, we should not consider them as two states, we should consider them as one state. This is what brings a factor of n factorial at the bottom. This is what solves the problem of Gibbs paradox in statistical mechanics, classical statistical mechanics, and that's what was used by Bose to describe the photons. Bose had difficulty in publishing this paper, as I mentioned, and he asked Einstein to help him. And if it is wrong, he wanted him to correct it or advise him if it is incorrect. So he was very, very obedient student. Imaginary, like Ekalavya, he was student of Einstein without being any student. What impressed Einstein was the symmetrization idea, and that was very brilliant. And he was very, very happy with that, and immediately translated it to German, and the paper was published. This idea, and there is a controversy about it, the Einstein, if you can apply it to Bose gas, which is actually both photons, you can apply it to hydrogen also. You can apply it to any other gas, helium. You can apply it to many other gases which are identical molecules, and which we know we get PV is equal to RT formula by applying statistical mechanics in the conventional way for all these molecules. But we have to apply quantum mechanics. We cannot be satisfied with classical mechanics, classical statistical mechanics. So in order to use the classic quantum statistical mechanics, first of all, you need to introduce this statistics where the counting of states has to be carefully done with symmetrization. And we should go to temperatures which are very, very low, okay, like 0 degrees Kelvin, close to that, if you want to see a difference between PV is equal to RT formula and our formula. This is what is standard thing which is taught in classic quantum statistical mechanics as a starting ideal gas. Ideal gas quantum statistical mechanics is what is taught. And this is the thing which is there. Now, if this is the status, then immediately ask the question, what will happen if you have a gas of molecules at 0 degrees Kelvin or very small temperature? All of them will go to the ground state because they are all symmetric thing, and more particles can go. There is no prevention, like another principle which I'm going to tell later. So this is what happened with respect to that. So this new state of matter, that you can form a condensate of Bose particles, the particles, molecules which obey the statistics, which is symmetrization, and that kind of a condensate is very, very useful and also correct. And we can actually predict, he predicted the existence of a condensate at very low temperatures. Now you have to go to temperatures of 10 to the power minus 9 degrees Kelvin if you want to achieve it. And it was achieved in 1995, around 1995, Bose-Einstein condensate was achieved. And some gases, very rare gases, where they don't interact, the molecules don't interact, they're all coming from some kind of rare non-interacting like helium and other things. So he used that and got, many people used and got the Bose-Einstein condensate experimentally. In order to achieve this, you need to go to temperatures which are 10 to the power minus 9. But this was predicted by Einstein using Bose's idea. So what was called those particles which obeyed Bose symmetry principle, are known as Bose-Einstein statistics. They are known as bosons. Photon at that time, we didn't know graviton was a particle at that time, but assuming that it was conjectured, even now we don't know. And now the new particle which is there Higgs particle, they are all examples of bosons. Okay, they are all examples of bosons. But in principle, any molecule which you have, if you can treat them as particle, even though it is extended object, they can have a statistics which is given by the Bose statistics, depending on its spin. Okay. Now what about fermions? Dirac discovered his equation in 1926 or 27 to describe electrons, because he wanted to connect quantum mechanics, which was known before, and relativity, which was discovered by Einstein. So relativistic quantum mechanics, he wanted it to be described. So Schrodinger equation is not a good equation for that purpose. So he wanted to write down a new equation which will describe the relativistic electron when it is moving with very high velocities. Now this equation came to be known as Dirac equation, and uses essentially very nice ideas from relativity and quantum theory. And what happened was, there is a large number of negative energy electrons. The energy of the electron can be negative also. So he introduced a new idea which was known earlier, the electron's negative energy C is completely full. It is completely full. So you can't put one more electron, because they obey a new statistics which is called antisymmetric statistics, or also known as Fermi statistics nowadays. So you can't put two electrons in the same state. This is the basic idea. That is, if you have two electrons, they have to be in two different states. This is the basic idea. Such a principle also required for filling electrons in the various orbits around the nucleus. We know atom is very stable. Now we have the periodic table in which hydrogen, the starting point with one electron going around in the first orbit. Helium has two electrons going in the first orbit. One is spin up and another spin down. Now you can't put one more electron in the first orbit because it is full. You have to go to the next orbit, which is L is equal to 1. L is equal to 0 is over. L is equal to 1 is there. There is, it can have M is equal to 0, minus 1 and plus 1. So there are three states with L is equal to 1. So that makes it 6 electrons are possible in addition. And 6 electrons along with the 2 electrons in the first thing will make 8 electrons in the shell, which is up to the first L is equal to 1 orbit. So this is the way the periodic table was understood and constructed. So this required the principle which was used, which was called exclusion principle, or which is coming from a statistics which is known as Fermi-Dirac statistics. Such a statistics is known as Fermi-Dirac statistics, and the particles which obey the statistics are known as fermions. Quantum mechanically, this is the meaning of that. Psi R1, R2 is the wave function of two electrons, two particles. We can write psi R1, R2, if you exchange, it will be psi R2, R1 with a minus sign. So it is not two different states, it is the same state. If R1 is equal to R2, then they will the thing will be 0. You can't put two electrons in the same state. The plus sign is for bosons and minus sign is for fermions. So this is what the two statistics which are there. We can write generally as psi R1 R2 is equal to e to the power I theta times psi R2 R1. If theta is 0, you call it boson. If theta is equal to pi, that my e power I pi is minus 1, and that's what you get here. So these are the giants who did that work. Earlier I showed you the picture of Satyendranath Bose and Einstein, who are responsible for Bose-Einstein statistics. The exclusion principle along with Fermi-Dirac statistics, this is the foundation for the Fermi-Dirac statistics, fermions. So Pauli is there, Dirac is there, Enrico Fermi is there. So these are the people involved. So we find is electrons, protons, neutrons, and all spin half particles, They're all spin half particles, because I told you electron has spin half. People later found protons also have spin half, neutrons have spin half. Very interestingly, even though it is a neutral particle, and you have they obey the Fermi-Dirac statistics. Photon, Higgs, pions, mesons obey Bose-Einstein statistics. So this is the content of two kinds of particles. One which obey Bose-Einstein statistics, symmetric statistics. Another which has Fermi-Dirac statistics. What you find very interestingly is all the particles which have obey Bose-Einstein statistics, they have spin 1 or spin 0 now. Or all the particles which obey Fermi-Dirac statistics, they obey they have spin half. Okay. There is a theorem known as spin statistics theorem, which says the spin half integral particle obey fermionic statistics, integral spin particles obey Bose-Einstein statistics. This is the theorem. So when we rotate a spin half particle like spin r electron by 2 pi, you rotate it about z-axis by 2 pi, you will not get the same wave function. You will get the minus of the wave function. Even though the probability is the same, probability to find the particle is the same, because e power the minus sign, psi bar psi whole square, psi dagger psi whole square, psi dagger psi is same. Probability is psi star psi. Okay, psi star psi is a probability, or mod psi square. So it will not change, the value will not change if you get minus sign, and that's what happens for spin half particle. The integral spin particle like spin photons, etc., if you rotate the system by 2 pi, you will get back like, if you rotate it by the third axis, z-axis, you will get it plus 1. So if you rotate a spin half particle by 2 pi, you will get minus 1. And if you rotate a spin integral particle, it will get be plus 1. And we know for bosons, the Bose statistic, if you exchange, you get plus. And for fermions, if you exchange, minus. So the interesting connection is the bosons and fermions, they are linked with the value which you get from rotation by 2 pi. Okay. So this is basically the theorem. Integral spin particles obey Bose-Einstein statistics. Half integral spin particles obey Fermi-Dirac statistics. Mathematically, we can write psi r1 r2 is equal to r2 pi psi r2 r1. If the particle which you describing is boson, that r2 pi will be plus 1. If it is fermion, they will naturally have spin half, and the natural value when you have spin half is r2 pi is minus 1. So the question is, what is the origin of this theorem? Why is it there? Where is it coming from? That is the question. Why is this mysterious connection? Integral spin particles obey Bose-Einstein, the same as Bose-Einstein statistic, and half integral spin particles obey Fermi-Dirac statistics. So the surprise is it is related to the topology, and I will try to explain. But before I explain what is the topology, it is a very simple answer. But what was the understanding of people before was the question. Initially, when relativistic quantum field theory was developed, they considered both integral and half integral spins. If you a course on quantum field theory, if you do, you will find that people talk with scalar particles, which are spin 0, and they will then talk about spinor particles, which is spin half, like electron, and then they will talk about quantization. Now, the quantization of these the fields which are described, quantum field theory, leads to infinite number of harmonic oscillators. Okay, that is the description for it. Infinite number of harmonic oscillators with ladder operators. If one assumed commutation relations among these infinite oscillators, A dagger is equal to plus 1, commutator is plus 1, and if you have two different oscillators, they commute. If you assume that kind of a thing, then the propagator one got is correct causality properties. What is the correct causality property? If you start a disturbance at a point and you go to a point which is space-like separated. If it is space-like separated, there is no way you can communicate with that space-like distance by a massive particle which we know. So if a particle, some disturbance is created here, you cannot affect a place which is far away, which is separated by a space-like distance. It's like saying, if I make a noise here, okay, you will get that noise only after a certain time, which is related to the distance traveled by from Madras to Chennai by electromagnetic wave from here to that place in this time scale which is there. The time is very short, but this is the basic idea. You cannot disturb a system here and get immediately, instantaneously somewhere else a response. Okay, so that is a kind of an idea. And that is what causality means in relativistic quantum field theory. And that is what the commutation relations for scalar particles will be required. So that gives you correct quantization and people are satisfied. Propagators are worked out, everything is nice. If the particles were half integral spin, they needed anti-commutation relation to arrive at the same result. If you want to arrive at the same result, you don't get it by commutation relation between the infinite number of oscillators. The oscillator should obey AA dagger. Anti-commutator is 1. Okay, anti-commutator is 1 and AA anti-commutator is 0 and A dagger anti-commutator is 0. This is what is required for proving the spin half nature of the particles, which is described by Dirac equation, Dirac action, etc. So now this gave mathematical confidence to the theorem, because causality can be understood in these theories only with correct commutation relations for the harmonic oscillator ladder operators which are there. Now that ladder operators AA dagger is equal to 1, regular thing, you can put any number of A dagger power n, okay, because there is nothing to stop it. Whereas if it is half integral spin, A dagger square is 0, A square is 0. So you can't put two electrons in the same state, comes naturally by the commutation or anti-commutation relations which you use for the photon, the scalar particle, spin 0 particle and spin half particles. The question remains, electrons and positrons are there. So this is a way in which we understood. So what is the understanding of relativistic, what is the understanding of this theorem is it comes from relativity. Relativity required the theorem, relativistic quantum field theory, in which you can understand the theorem and the connection between them is due to that. That was the understanding people had in 1930s. But then people started asking, electrons and positrons are there even in non-relativistic physics too. We did Stern-Gerlach experiment. When they did, the energy or velocity of the electrons are too small to be considered that you need relativity for that. So conduction in metals or atoms, when you have hydrogen atoms, those electrons are going with energies or velocities which are much smaller than the velocity of light. You don't need relativity to describe hydrogen atoms. Schrodinger equation describes it very well. So why do you need relativity to understand the spin statistics theorem was the doubt which was there always in the minds of people. So the doubt remained that it is not due to relativity via the spin statistics theorem, and much must be deeper origin. So now comes the meaning of identical particles. Particles are characterized by mass, charge, and spin. Spin is denoted by a direction. You need to describe spin is, how do you describe spin? It is pointing in one direction. So you need a spin. To describe a spin, you need a direction for it. So if it is spinless particle, you don't need direction. It's only a part, the size of the particle is enough, it can be very small, etc. One can visualize a small extension and a rotation about some axis. So if you have a direction, I can rotate the direction about some axis always. So that is the way we understand that particle with mass which has a spin, even though it is at rest, it has a spin and it is having a direction, and that direction can be rotated about some axis. So there is a rotation about some axis which is always there as long as the spin is associated with that particle. If such a particle is rotated, it will have two different behaviors depending on the spin. If the spin is integral, a rotation by 2 pi will bring it to the original state. If it is half integral, then it will require 4 pi rotation to come back to original value of the state. The state is described by the wave function, but the state, even if you rotate by 2 pi, the probability density will be completely the same. Don't have to worry about it. But the wave function will pick up a negative sign. So this is what 2 pi rotation will do it. This is because of the peculiar behavior of what we know now in group theory as a behavior of what is called the rotation group. The rotation group is specified by what is called special orthogonal group in 3 dimensions, SO3, and this has this kind of a behavior. For statistics, we need two identical. See, for spin, it is enough to describe one particle. You don't need two. One is enough. For statistics, we need two identical particles which are exchanged. We can establish exchange is topologically same as 2 pi rotation of one of the particles. So this is the basic idea, that you can establish exchange of two particles is similar to, topologically it is same as 2 pi rotation of one of the particles. This will not need relativity. You don't need relativity, but we need existence of antiparticles. Now electrons are there, positrons are there, even in non-relativistic physics. They are together in relativistic physics, but electron and positron are there even in non-relativistic physics. So this is basically the idea. So I'm going to explain how the topology comes in. So there are two diagrams here. Concentrate on the left. The left diagram, we have somewhere from time minus infinity, a particle and antiparticle is created on the left hand side, and they start moving. The vertical axis in this diagram is time. The vertical axis in this diagram is time. At time minus infinity, there are no particles. At some time minus t, you have a particle and an antiparticle created. So they try to go in different directions. They go in different directions. There is another particle and another antiparticle is created, which is the diagram which is showing you. Now I take the particle which is on the left hand side, okay, with the particle on the left hand side, on the two particles and two antiparticles are there. I position the two antiparticles at the corners, or the left corner, left and right corner, and the two particles are on the middle two particles. They are middle two particles. I want to make them identical. Now I give the same mass, same momentum, and I exchange them. And that is the diagram which I have explicitly shown here. And then after exchanging, I annihilate them back at some plus t, and then after that you go to vacuum state. So you have a vacuum state where particle and antiparticle is created, two particles and two antiparticles are created, and the two particles are exchanged, and two particles are annihilated, and they go to vacuum state. That is what the left hand side diagram is. Now if you take this is a belt. If you take the belt and just, if you want to remove that wriggle which is there in the middle, you will get the right hand side. The right hand side diagram, that wriggle which is there, you can even try it with your piece of paper or your belt. You will find that it is, the right hand side becomes what you have. What is that diagram? It is a particle, antiparticle is created, The particle is on the right hand side and it is rotated by 2 pi rotation. After 2 pi rotation, it is annihilated with the antiparticle, and this is what you have here. So this diagram, which is saying that exchange of two particles topologically is same as rotation by 2 pi of one other particle which is there, is what this diagram is saying. So this two equivalence of these two diagram is exchange is equal to rotation by 2 pi is what this diagram is explaining. Right hand side is if we unwind the process as a belt, what we have is a rotation of a single particle by 2 pi. We have the spin statistics theorem. R2 pi, rotation by 2 pi is exchange. If the particle is boson, R2 pi is +1 and exchange is +1. If the particle is spin half, R2 pi is -1 and exchange is also -1. So this is the fundamental origins from where this whole thing that exchange is equal to rotation by 2 pi is emerging from topological behavior of a particle with spin. A spin has direction. Don't forget, spin has direction. And that direction is to be seen in this language. So you can ask a question, can we go beyond Bose-Fermi statistics? So this is the basic question which I'm going to explain in the next 5 minutes, and then I will be ready for any question which you want to ask. So you can ask a question. So this is Bose particles obey +1, Fermi particles obey -1. Bose particles have integral spin and Fermi particles have half integral spin. Now, if I want to go beyond Bose-Fermi statistics, we have to see whether it is possible to have beyond angular momentum also beyond that. Is it possible? That is a question. Answer is, it is possible in 2 dimensions. So in 3 dimensions, with the definition, probability amplitude is given by a complex number. Probability amplitude is a complex number xi. Psi is the probability amplitude, and psi square, mod psi square, is the probability. With the freedom to change only the phase, we have only the phase that can be chosen. Psi is probability amplitude, probability is psi square, e power I theta times psi is same, and with that there are only 2 choices possible, and that is boson and fermion. Now in 2 dimensions, we have more choices possible, which are known as anionic statistics. Again, already due to topology. This is also very interesting. Now in 2 dimensions, the rotation group is what people call the rotation group in 2 dimensions, SO2 instead of SO3. Orthogonal matrices in 2 by 2 orthogonal matrices. Unlike 3 by 3 orthogonal matrices, whose representation theory is given by the regular angular momentum theory with integral and half integral spins, in SO2 rotation group in 2 dimensions, the representation theory is given by any value of theta. It can be, the rotation can be given, representation is given by any value of theta, e power I theta, and there are no half integral or integral spin alone question that will emerge. So in 2 dimensions, angular momentum can have a value which is not specified by the half integral or integral spin. It can be specified by a value which is theta. And if you do the same for 3 and higher dimensions, it will remain. So this is basically the reason for that is topology. The reason is the following. If you take 2 dimensions, if you assume a sheet of paper and if you make a hole in it, that hole, if you want to go around it, you cannot, there are some loops which can be contracted, some loops which cannot be contracted, and that is why we call that space as multiply connected, infinitely connected space. But that doesn't happen for 3 dimensions. You go to 3-dimensional space and remove the origin. You remove origin. But if you have a loop, you can always bring the loop above and contract it. There is no difficulty in doing that. It is still simply connected. So that is what makes the difference between 2 dimensions and 3 dimensions. This leads in 2 dimension. We can have a statistics known as anionic statistics, which I have written in equation 1 here. Psi r1 r2 is e to the power I theta psi r2 r1, and the theta can be anywhere between 0 and pi. Actually 2 pi is not required, between only, because you will still have mod psi square, and this is the thing you need only from 0 to pi. Now this is what we have for statistics. What about angular momentum? Angular momentum can also be in 2 dimensions fractional because of SO2, and the theorem says R2 pi is equal to exchange. Is it still possible? The answer is, very interestingly, again topology. What in dimension 3 and higher, we have identical particles and indistinguishable particles, and exchange gives the same state. The exchange symmetry is what is known as a permutation symmetry. They can be easily divided into 2 classes, even permutation and odd permutation, and that is what is actually giving rise to the possible statistics being Bose statistics and Fermi statistics. Now in 2 dimension, the symmetry when you exchange particles is given by what is called the braid group. The group is not permutation group, it is a braid group. What is braid group? It is the usual braids which we know, our girls, young women, and now men also, they have the hair and they tie it up in strands and cross one strand above another and make a braid, and that is what is drawn here. Now braid is essentially, you have several strands. You can take the strand one above the other or one below the other, and there are 2 different ways in which you can go about, and that is what the braid group is going to come. Now the symmetry is no longer permutation symmetry, and the symmetry is called the braid group symmetry. And the representations of this braid group symmetry is there are infinite element group even for 2 strands. Even if you have 2 particles which is going to evolve in time, you can go one above the other, which means one crosses the other and comes back, then you cannot contract it to identity. This is the thing. If you exchange and exchange it twice in 3 dimensions, is identity operator. In 2 dimensions, it is not identity operator, and that is what the braid group is telling you. And this is what is the braid group, which I have drawn as a diagram, which is well known. I'm not going to explain it because it will be a course by itself, but what you have is this braid group also has parameter theta to tell you the exchange. The thing is given by e power I theta. So this kind of particles can exist in 2 dimensions. Do they really exist? So now we know quantum Hall effect in 2 dimensions. A lot of experiments for the past 25-30 years have been happening. You essentially have restrict the particles, electrons, to remain only in a plane, and then try to apply a very high magnetic field and look at the particle, the theory of that, and it leads to possibility of anions in 2 dimensions. Now 2-dimensional anions have become very popular now because they can be used as quantum units in quantum computer. This is a very interesting new application which has emerged. So now I'm going to end up with my last slide is here. This is my last slide. Can we go beyond? Answer is yes. If you define the probability is amplitude is given by a complex number. That is what we do. Function is a one complex number, probability amplitude. Now you extend it beyond that. You go to a complex number, but a column of complex numbers, psi1, psi2, psi3. It can be a column of 2 numbers, psi1, psi2. It can be a column of psi1, psi2, psi3. If these things are possible in an effective theory that you have, then the probability will turn out to be psi dagger psi, and this kind of complex column which you have you can have unitary transformation. Side dagger side, you can make a unitary transformation U on the side and U dagger on the left hand side. You will still get 1. So the transformation can be given by a unitary transformation, and it can lead to what is known as non-abelian statistics. So that is what is a new thing which is there, and this is also something people are excited about it in the last 20 years. And we, at least myself and my colleague in math science, was one of the people who proposed this idea in our old paper in 1989, that it is possible to have in a model that you can have non-abelian statistics. So with that, I'm going to stop and I'm going to end with this. Thank you. If you have any question, I would be happy to answer.
TRG.
Yes.
It was not very clear, the equivalence of, exchange and
Yes.
what was that thing? Can you come?
Yeah, here. Sorry. Theorem. You want the theorem?
Last.
This one?
A diagram.
Diagram. Where? Here. This one.
Yeah. The previous one. Yeah, next.
So next. Okay.
Yeah, this one.
This one, this is a break group. You wanted this.
Yeah, this one.
Okay.
Yeah.
Yes. So what you do is you take a belt. Okay. Now you can join the belt in the conventional way, which is like a cylinder. Okay.
Okay.
Now instead of joining as a cylinder, you rotate it by 2 pi and then join. That will be the right hand side diagram. Rotate it by 2 pi and join. Now if you look at it carefully, it will look like what you have on the left hand side.
Okay.
You have a belt with you, you can try it out.
So
You can take one sheet of paper and do it also. Ordinary sheet of paper.
Do you need antiparticle for that thing?
Yes. Hello.
Do you need antiparticle to? You mentioned that there should be antiparticles also.
Yeah, because see, the thing is, I want to create the particle and antiparticle and rotate the particle by 2 pi and annihilate it. I want to compare it with vacuum to vacuum state. So that's what makes. Otherwise, if I take only a particle and rotate it by 2 pi, I don't have a way of comparing topologically with the other thing. So I need this process. If I have an antiparticle existing separately and particle existing separately, which can, then they can rotate by themselves without doing anything. Now, if I want to compare it with the exchange, I need 2 particles. Whereas particle rotation is by only 1 particle. So in order to do that, I need 2 particles. And if I want 2 particles, I need 2 antiparticles and then collapse them. Or I can have a particle and 1 antiparticle and collapse them. In between, I can do the exchange or rotation by 2 pi. I can do exchange or I can do a rotation by 2 pi. Both will be topologically the same. This is what people call, actually, if you Google belt trick, if you do belt trick in Google, you will find a lot of YouTube videos actually giving this belt trick, and you can actually see it. I wanted to download and keep it so that you can see it.
What will be the situation if it is a self-conjugate particle?
Which one?
Self-conjugate, for example, photon.
No, well, so that is the thing. So we don't really need antiparticle in that sense. If their particle and antiparticle are one and the same, which means it is able to annihilate. That from vacuum you create 2 particles in that case. So it doesn't matter. I want to compare it with this kind of a diagram. I compare from vacuum, I create 2 particles, and exchange 2 two different particles and then exchange, or I rotate it by 2 pi. It doesn't matter whether thing, but only thing is such a possibility that the negative energy kind of thing which is there, or particles going in opposite direction with time negative thing, which is a Feynman way of saying, is required. So this is basically, so that is why we need to argue about it in this way, that you are right. Actually, that is one of the confusions people have. So the basic idea is that I should be able to create either part, if it is particle and antiparticle are one and the same, I should be able to create two particles. Or if it is particle and antiparticle are different, I'm able to create it as a pair and annihilate it. That's the way what I'm looking for is topological development of vacuum to vacuum amplitude, or vacuum to vacuum amplitude. That's what is, and I see topologically that is the object which you get here.
In your notation, R is for rotation matrix, right? Is it,
yeah, SO3 rotation matrix.
Matrix, okay.
Yeah.
Finally, suppose you take Majoran or neutrino, does it create any problem if you do this thing?
That is a very good question. It will not create problem. It will also obey Fermi-Dirac statistics.
But particle and particle are the same.
Yeah, they are one and the same, but it's still spin half. So you can create from vacuum two Majorana spinors. That is the point. That's the point. It's not only Majorana spinors. Even other thing, there are particle and particles are same even for many other cases. Other cases also. Some K-meson or something is there.
Okay, thank you.
Okay.
There are some questions in the chat box. Please see.
Okay, chat box. Okay, let me go to the chat.
The questions are asked by Sadish KP. Maybe Sadish can ask the questions directly, if possible. Sadish KP, if you are available, please ask the questions. Otherwise, I will.
Okay, all matter fields produce fermions and mediating fields bosons. Do we have deeper reason for that? How is the braid group defined in a disconnected 2D topology?
No, there are two different questions.
Yes.
The first one is that
question. Okay.
if you take all matter fields, that will be fermion. And if you take mediating particles like gluons, photons, etc., they will be bosons.
Okay. Now there is a particle which is called Higgs particle.
Yeah, that is okay, but
that is also that's not a.
Apart from that.
So there are. That is one of the questions. In fact, it will be interesting. We don't have a deeper understanding of why all matter is fermion, and generally all. But one thing is bosons are there, which are matter also. We have mesons are there. Okay.
But they are not elementary. If you go to the quark level and treat quarks and electrons, leptons of the matter particles, quarks and leptons, they are always fermions.
That is true.
But the other bosons are other mediating, interacting fields correspond to bosons.
That is true. We don't have a good understanding of that. Except the mediating particles, we essentially start with massless particle. Okay, so the massless particle.
We have the W and Z bosons, which are massy.
Yeah, but you give mass to that. You start with massless and give mass to that by spontaneous symmetry breakdown. Now, if you have supersymmetry in the theory, let me come to that. If you have supersymmetry, there are exchanging particles, but super partners, and this symmetry is broken there. Essentially, you have matter whose partner is spin half, integral spin. For example, photino, they call it photino, and gluino, they're all there. and also for correspondingly the S quark or S neutrino, S electron, they are also there. So we know as of now that all the particles are matter is mainly fermions, and all the mediating particles are bosons. That is why we have not yet discovered supersymmetry. We have discovered half of the supersymmetry, which is what we have given up. We don't know, but this is one of the deeper questions.
But TRG,
Yes.
if you want to retain the fermionic property of something, the emitted particle has to
Every?
suppose the interaction is due to emission of some exchange of some particle.
Okay.
So if you want to keep the fermionic property of a particle, the exchanged particle has to be boson, right? Otherwise spin will not be conserved.
Well, angular momentum, you can talk about that way, conservation of angular.
I mean angular.
Yeah, angular momentum, yes. If you want to create angular moment spin half particle, from a spin one particle, you need to create two of them.
Yeah.
So two spin halves are required, otherwise you cannot do that. That will be there. And that will also go along with consistently with statistics also. It will go consistently with statistics of those particles. So there's no problem. So it is, there is another question by Satish. Break group defined a disconnected 2D topological space. Yes, we can define. I myself have used some of these things. You define break group on a sphere S2 or arbitrary genus part spaces, and even disconnected spaces you can define and it can be used, but it will become only mathematical mathematically it is possible to define, whether practically to be useful, I don't know. So that is a problem with that.
That is, if you define that Dirac bulk business, that is there only for a connected space. If the space is disconnected, that Dirac bulk business, I think, will not work properly.
No, then there will be no. If the space is disconnected, then there will be a topological quantum number which keeps the space, the particles only in one part of the space.
Oh, that means you have to introduce one more quantum number.
Yeah, that will be there. That has to be included.
Okay. Thank you.
Okay. So there is
the other one is simple.
One more non-relativistic fields like Schrodinger field. We have both fermions and bosons. Relativity need
is relativity needed. That is you take a Schrodinger field and condense that, you will get both fermions and bosons.
Yeah, we can have, but one thing is whether the link to the angular momentum spin of the particle was not clear. So Schrodinger equation is an electron without its spin. That's what Schrodinger equation is. Otherwise, you have to talk about Pauli equation. Non-relativistic theory, we have to talk about what is called Pauli equation, which is spin half as well as it looks like Schrodinger equation. We have to talk about that.
So can I ask a question?
Yes.
So we talked about the Bose-Einstein condensate. Can there be a fermionic condensate? As I've seen a couple of things like in superconductors, you can have this fermionic condensate. So how do you comment on that?
Well, the Fermi that they form what is called the superfluid or superconductor. So what they do is essentially two fermions. They join together and form a boson as a composite object in over a distance, like BCS pair, and then they can condense. After becoming boson, they can condense. So this is what is used in several ideas. So the condensation, Bose-Einstein condensation is for Bose particles. For Fermi particles, they have the superfluid nature, which is coming, superconductivity nature, which is obtained by, to the extent we know now, by forming the pairs. And the pairs condense together as a boson. So that kind of condensation can take place.
So the particles in the pairs are spatially separated?
They are spatially separated. So it is entangled if you want.
Okay, that leads to another
Very complex object. It's a very complex object. Yes.
Okay, that leads to another question. My question might be quite silly. For what example, like if you take a star and if you're trying to compress it, like creating a black
Yes.
hole in the end, like most of the stars are staying there because of the degeneracy pressure, like you can say, because of this
Yes.
exclusion principle and so. But
Yes.
in the case of the black hole, everything is condensed or collapsed into one singular point. So the spatial separation is effectively, I don't know whether we can say it's zero.
We
But
can't say
then,
it is zero, but there are a lot of new physics which come into the being. Since you have asked this question, I will tell you one work which we have done recently. This is about, you don't have to go to black hole, but that statistics is used, Fermi-Dirac statistics, for explaining white dwarf, which is Chandrasekhar himself has done about 70 years, 80 years back, 90 years back, 1930s. So what happens is a star like sun, it uses nuclear energy, and that gives the pressure. Otherwise, if the pressure is not there, all the matter which is there in the sun will collapse inside. So the pressure is created by the nuclear fusion which is happening, which balances the gravitational force. So if you take a very large star with, say, something like 10 solar masses, it will collapse after nuclear fusion is exhausted. All the nuclear fusion is exhausted. Now what will happen at that stage is there will be a core which is there, and that core there is no nuclear fusion, but the electron gas is there. So there is a new pressure which is coming in, which is coming from the degeneracy pressure of the electrons, which is Pauli exclusion principle. This pressure that no two electron wants to stay together is balanced by the gravitational force, which is the gravity force, and that can form a star. And the possibility of such a thing was worked out by Chandrasekhar in 1936 or 37, which essentially says that if the mass of the white dwarf is less than 1.4 solar masses, it will form a white dwarf and stay like that forever. It's like a dead star. Now this is what he gave, and if the mass is much greater than this, something like 10 solar masses, 4 solar masses, 5 solar masses, then the electron degeneracy pressure is not enough, and it will collapse even further, and you will form what is called the neutron star up to 3 solar masses. If it is a mass is greater than 1.5 but less than 3 solar masses, it will form. Now beyond that, it will form a black hole. So these are all assumptions using only classical general relativity. And quantum mechanics is used in a very, very loose way without any quantum theory except the strategy. So now you can ask a question, if it is possible to have a white dwarf which is greater than 1.5 solar masses. Apparently there are some evidences which are there, which is up to 2.6 or 2.5 solar masses, there could be white dwarf, but it is still inconclusive. But if it is there, violating Chandrasekhar limit, you can ask the question, how is it happening? So this is one work which we did recently, about a year back, which is that the statistics of the particles, when they are, if you are looking at the density of particles, electrons, which are very, very high. Just for comparison, I will tell you the white dwarf density is 10 power 6 grams per cc. There are 10 power 6 grams per cc. So the inter-electron distance at that time is something like Compton wavelength or slightly more than Compton wavelength of electron itself. So you find that the electrons behave as identical particles separated by that. But Compton wavelength is a scale. If you go two particles, electrons closer than the Compton wavelength, then particle-antiparticle pairs can be created, because the energy, because of this thing togetherness, makes it possible that you can create particle-antiparticle. So you find that if you have an electron, two electrons, if the distance is too small, less than Compton wavelength, then you can't call it as two particles being exchanged, because there could be a particle and a particle-antiparticle pair in that small location, and similarly for particle-antiparticle, the other location. And when we talk about exchanges, it becomes much more complicated exchange which is happening. That leads to what is known as a geometry, which is known as a non-commutative geometry, which we have used earlier. And I use this notion that electron in these length density scales, densities of the order of 1/100th of Compton wavelength of electron, if the particle densities, particles are less than 1/100th of something like 1/10th or 1/100th of Compton wavelength, the behavior of electrons, even though they are not assuming there is no electromagnetic interaction, identical particles become much more complicated and leads to a new kind of physics, and leads to this kind of possibility that it no longer, you cannot characterize them as fermion, because it is not one particle, it is actually 3 particles or 5 particles, and you are exchanging them together, and that makes the statistics a little more complicated, and the electron no longer behaves like Fermi particle in these length scales. Even in ordinary length scales like atom and etc., the distances are too far away and they behave like identical particles. But in the length scales of this nature, very high density, the possibility of changing the statistics arises in a new way, which uses gravity, which uses quantum physics much more than what we know already. And the new possibility is it can go up to 2.6 solar masses. This is what we have as a model extending the work of Chandrasekhar, but this is the kind of a thing. Now you can ask a question, what happens in black hole? This is the question which you wanted. And that understanding black hole formation, whether it is a thing, etc., whether it is really formed, etc., at that fundamental scales which you are talking about is still, we don't know quantum gravity. We don't know gravity with the quantum theory. We do not know. So this is what the current status is.
Okay, thank you, sir. So in short, what you mentioned is if I take 2 electrons together and try to bring it as close and close and close, if the length scales are very, very small, the electron will behave differently than what we have experienced so far.
Yeah, definitely.
Okay, thank you, sir. Thank you.
Sir, I have a question.
Yes.
You have mentioned anions can be used as quantum bits or qubits in a quantum computer. Okay, what property do you think that makes it interesting candidate for a qubit?
Okay, what is used there is, supposing there are 2 possibilities, anion, because this is coming from topological property of the particles themselves. So the entanglement which is there between 2 anions, another thing, is topologically stable. It is topologically stable, and that quantum computer, which require coherence and other things, can use this factor, which was not possible with the other cases. See, the coherence was getting affected in regular qubit situation because of the noise which can destroy it. Now with this kind of thing, there is possibility at the theoretical level. People have not succeeded. There are people who are trying to construct chips or quantum, some equivalent of qubits using the possibility of anions. And I do not have better understanding of that as of now. But the other possibilities, nano-Abelian statistics also can play a role. But we don't know. These are all theoretical conjectures which people have used as of now.
Thank you very much, sir.